This is the first lesson of Unit 2, which is going to be on quadratic equations. Specifically this note, we're going to talk about modeling those quadratic relations. So the first part here is an activity. It says, plot the points and draw the graph for each of the relations below. So the main thing here to remember is that obviously your x coordinates are the first coordinates, y is the second, and knowing that the horizontal line is your x-axis and the vertical line is your y-axis, and we can see that they are labeled here. You've obviously been plotting points on graphs for quite some time now, but sometimes we get kind of confused and end up plotting the points backwards, so it's important that we don't do that and we are plotting things correctly. So 4, -3 is the first point, so on my x-axis I go to 4, and then I go down to -3 and put a dot. And mine is going to be messy just because of my tablet here, but you hopefully will get the point. Then we have 5, 0, so 5 on my x, 0 on my y, 6, 3, 7, 6, and 8, 9. Okay, so once we have those points, what we need to do is we need to draw a line through them. Again, yours will probably be better than mine. It should look something like that. Okay, and then just as a habit to get into, we've plotted those points, but that doesn't mean the line ends there, so we need to get used to putting arrows on the end of the two sides of the line there. Okay, so now let's plot these other points. So we have -1, -3, 0, -4, 1, -3, 2, 0, and 3, 5. Okay, so then we will draw a line to connect those dots again. Mine's not going to be perfect, but just bear with me. Oof, the end there got a little messy, but you get the point. Okay, so it's going to look something like that. Just erase beside. Oops, color that back in. Just as bad. Oh well, you understand the point. Okay, so there is kind of half of our parabola, so we can make the assumption that the other side would look exactly the same. So we would plot symmetrical points. So there would be a point there. What do we have? 2, 0, and then we had 3, 5. So that would be the same. It would be -3, 5. And then we could kind of assume that the other half of our parabola would look something like this. Okay, so they should look symmetrical. All right, now that we have done that, let's talk about the difference between linear and quadratic. So the graph of a linear equation is y equals mx plus b. Okay, and this has kind of been the focus of math up until this point for you, so that should be familiar. If our equation is in that form, we have a straight line. So that's modeled in that first graph here. Okay. On the other hand, if we have the graph of a quadratic function, that equation is going to be y equals ax squared plus bx plus c, and that is going to be a parabola. And parabola is just the word we use to describe the shape we can see here in graph number 2. So again, we only graphed kind of half of the parabola, and then we shaded in the other side with that yellow, but that entire shape altogether is that parabola shape. Okay, so let's move on. Let's talk about first and second differences. So first differences, for evenly spaced x values, find the difference between consecutive y values. Okay, so that's how we find first differences. So before I go on and define second differences, let's do that with our first table here. So this is our first table here. So what that is saying is that we need to, anytime we see the word difference, it means subtract. So what we're doing is we're going to take the second and subtract the first. We're going to take the third and subtract the second, etc. Okay, so we have 4 minus 7, which is -3. And we have 1 minus 4, which is also going to give us -3. We have -2 minus 1, which is -3. -5 minus -2. So remember, that's that double negative there. So that's going to be the same as plus, right? We can assume those two negative signs will make a positive. So it's the same as -5 plus 2, which also gives us -3. And lastly, we have -8 minus -5. Again, that double negative turns into a positive, and we get -3. Okay, so all of those first differences we can see are the same. Okay, so what we would write is first diffs are constant, which is the same as the same. Okay, so first differences are constant, so the relationship is linear. Okay, so anytime those first differences, when we find them and they end up being all the same number, which we can see these are all the same number, right? That means that we have a linear relationship. Okay, so that's how we find the first differences. We just subtract. Okay, to find the second differences, we need to determine the difference between consecutive first differences. Okay, first differences. And the key here too is that on the left-hand side, your x values here need to be going up by the same thing each time as well. Okay, so you can see we're going up by 2 each time. Okay, so that's why we can find those first differences. So same thing for the second chart here. We're going to find the first differences and then the second differences. So just like before for the first differences, you take the second, subtract the first, the third, subtract the second, etc. And I like to just make these little lines to indicate kind of what I'm subtracting. So the first one, I have -1 minus 0. That gives me -1. Then I have 0 minus -1. Again, that double negative just means adding. So it's 0 plus 1 is 1. Then I have 3 minus 0, which is 3. 8 minus 3 is 5. And 15 minus 8 is 7. Okay, so we found our first differences the same way we did in that first table. Obviously, we can see that those first differences are not all constant, right? They're not all the same. So we're going to move on and find our second differences. And I'll just do that in a different color. Okay, it's going to be the same process, except we're using our new numbers here. So the second subtract the first, the third subtract the second, etc. So now we have 1 minus -1, which is 2. 3 minus 1 is also 2. 5 minus 3 is also 2. And 7 minus 5 is 2. Okay, so we can see now that those second differences are constant. So when the second differences are constant or the same, that means it is quadratic. It is quadratic. Okay, remember quadratic is when we see that parabola shape. Okay, so moving on to the second part of our note here. I'm going to start with a couple definitions. Bear with me, I'm going to try to write as neatly as possible so that you can read this. Okay, so the definition of a parabola, which we should kind of know from that last page, is a symmetrical U-shaped curve. Okay, the vertex is your lowest or highest point on the parabola. Minimum is the lowest point in a parabola or on a parabola that opens up. That opens up. Okay, your maximum, on the other hand, is going to be the highest point on a parabola that opens down. Okay, so moving on from these definitions, it says linear or quadratic. How do we tell? Okay, so if we have a graph and it's parabola, we know right away that that is a quadratic. If the first differences are constant, as we saw on the last page of the note, we know that it's going to be linear. If the second differences are constant, again, as we saw on that other piece of the note, then we know that it is a quadratic relationship. If the degree of the polynomial is 1, so if it only has an x term, okay, there's no x squared term, just an x term, then it's going to be linear. If, on the other hand, the degree of the polynomial is 2, or if it has an x squared term, we know right away that it is quadratic. Okay, let's move on to the activity. So for each example, evaluate or estimate for x equals 2 and identify whether it is linear or quadratic. Okay, so first things first, let's identify whether these are linear or quadratic. So based on that information we have above here. So I'm just going to follow that information step by step. So if the graph is a parabola, okay, well, I can see D here has that U shape, so that's a parabola, so that one must be quadratic. If the first differences are constant, okay, I can't really see that straight up from the information I'm given here. I can't see the second differences either. If the degree of a polynomial has an x term only, okay, so there's no x squared term, so I can see right away that B here must be linear. Okay, and then if the degree of the polynomial is 2, so if it has that x squared term, I can see that A has that squared there, so this one must be quadratic. So I just have one left, and this one we defined on the other page, right? If we have a straight line, we know that it has to be linear. Okay, so it says, so we've dealt with this. We've identified whether they're linear or quadratic. The other part is to evaluate or estimate for x equals 2. What that means is to substitute. Okay, it's saying instead of putting x, put 2. Okay, so the reason it says evaluate or estimate, obviously with our equations, we can't estimate, right? We have no idea unless we actually evaluate those. But for our graphs here that we have that visual, we're just going to look when x equals 2, what does y equal? So let's start with the graphs because they're going to be a bit easier. So I'm going to zoom in here for you. So for C, so it's asking us to estimate when x equals 2. So again, you need to know that x is that horizontal axis. You're going to kind of draw like a little bit of a line up from 2. Again, mine is not going to be perfect. Okay, so that's that point right there, circle it in green, is where x equals 2. So in order to figure out what our y value is, I'm going to draw a line over to the y-axis. Okay, and this is asking us to estimate. So as you can see, my line hits somewhere between 2 and 3. Whoops. But because it's so close to 3, I'm just going to say that y equals approximately 3. Okay, so if x equals 2, y equals 3. Okay, and like keep in mind that that means the coordinate is 2, 3, right? X, y. And that's how we would plot that point that I have circled in green. All right, moving on to D here. So again, we're estimating when x equals 2. So what I'm going to do is I'm going to try to draw a line. Oh geez. Oh my gosh. Okay, hang on. I'm going to get my actual line out. Make it easier for me. Okay, so it's going to look something like that. So as you can see here, we aren't actually touching the line, right? So that line would obviously be extended. It would keep going. So the next thing I'm going to do is draw my line over to about there. So as you can see, my scale stops, right? But I'm going up by 1 each time, and you can see that this distance here looks approximately the same as these distances, right? So we can assume that when x equals 2, y is going to equal approximately 5. So y equals 5, and again, just relating that back to coordinates, that means our coordinate here is 2, 5. Okay, so those are the easy ones when we actually have a graph. Going back over to the left here, dealing with A and B, I don't have a whole lot of room, so again, bear with me. Hopefully I can write this out clearly. So, like I said before, when we're evaluating, that means we're just replacing x with 2. So the first step is just to replace it. So I'll have y equals -3, 2 plus 1 squared plus 1. Okay, at this point, it's just a matter of following BEDMAS, right? So we start with our brackets. We have -3 times 3 squared plus 1. Next is to deal with our exponents. 3 squared is 9 plus 1. Okay, obviously the next step would be to do that multiplication. So -3 times 9 plus 1. So you can do it all in one, or you can do it as step by step here. So -3 times 9 is at -27 plus 1. So y equals -26. Okay, so if we had that on a graph, again, relating it back, that coordinate point is 2, -26. Okay, so we're going to do the same thing for the second part here. Okay, we're going to, instead of writing x, we're going to replace that with 2. This one's going to be a bit more work because we can see y isn't isolated, right? So we're going to have to get y all by itself. So instead of writing x, I'm going to start by writing 2 in that spot. Again, it's a good habit to put it in brackets so you remember that that is multiplication. So we have 2 times 2 minus y plus 7. Okay, so I can simplify that. I have 2 times 2 is 4 minus y plus 7 equals 0. But remember, I need to know what y equals here. So what I'm going to do is I'm going to rearrange my equation so that my y is all by itself. Okay, when I cross that equal sign, remember the sign in front of whatever you're moving changes. So that negative y is going to become positive y. So I have 4 plus 7 equals y. So 11 equals y. And again, remembering that that means on our graph, if we were to graph this, we would have the point 2, 11. Okay, moving on to our last example here, we're going to do an application problem. So it says a football was thrown in the air. Its path can be modeled by the relation h equals negative 5t squared plus 20t plus 1.5, where h is the height of the football in meters and t is the time in seconds. So it says the first thing we want to do is complete the table of values and graph the relation. So in order to do this, what we need to do is we need to take these values of t and sub them into our equation to solve for h. So sub in t and solve for h. Okay, so exactly what we did before, we're just now incorporating this into a new context. So I'm going to show you a couple. I'm not going to have a room to show you all of them, but hopefully after seeing a couple, you would be able to find h for the other ones. So the first value of t is 0. So that means I'm going to replace t with 0 in my equation. So I have h equals negative 5 times 0 squared plus 20 times 0 plus 1.5. Anything times 0 is going to be 0, right? So 0 squared is 0. 0 times negative 5 is 0. Plus 0 plus 1.5. So h equals 1.5. So I'd write in here 1.5. Okay, next I have to find h of 1. So I'm just going to draw a line between so I can separate them. There we go. Okay, so now h of 1. So h equals, remember that just means you're replacing t with 1. 1 squared plus 20 times 1 plus 1.5. So 1 squared is just 1, and anything times 1 is just that anything. So this will be negative 5 plus 20 plus 1.5, which will give us 16.5. Okay, so again, you go over here and you plug that in for your h, 16.5. All right, we'll do one more. Obviously, you would have to do them all to figure out the points, but again, I'm just showing you one more. So now we're going to find h of 2, so we replace our t's with 2's. So 2 squared is 4, right? 4 times negative 5 is negative 20. 20 times 2 is 40, plus 1.5. And that will give us 21.5. So again, we'd plug that in over here, 21.5. Okay, and you would do the same for 3, 4, and 5. Again, I'm out of space, so I'm just going to tell you what those values should be. So if you plugged in 3, you should get 16.5. If you plugged in 4, you should get 1.5. And if you plugged in 5, you would get negative 23.5. Whoops. 0.5. Okay, so what we've done is we've now created those coordinate points, right? The t is the same as our x, and the h is the same as our y. So we have 6 coordinate points that we need to graph on our graph here. So again, you're just drawing or like making a dot on those points and then connecting them. So we have 0, 1.5. Because these are decimals, you're going to have to estimate a little bit on the placement. 1, 16.5, somewhere around there. 2, 21.5. So approximately there. 3, 16.5, so we're back at that 16.5. 4, 1.5, so that's down back over here. Okay, and then 5, negative 23.5, we just can't plot because we don't have that on our graph. So the next thing we need to do is connect those dots with a line. Okay, as you should be able to see, it should be pretty symmetrical. Okay, so it should look something like that. And we can see that this is a parabola, which makes sense, right? We should have known it's quadratic simply because we had a squared term in our equation. Okay, so part B says use the graph to estimate how long the ball was in the air. Okay, so we simply have to look at our graph, okay, remembering that our x-axis is time and our y-axis is height. So obviously, the ball was thrown. It starts at 0 seconds. Okay, so we can kind of follow the path. It's going up. The maximum height that it reaches is 21.5, and then the ball starts to come down. Okay, obviously, as soon as we cross that x-axis, the ball is going to be on the ground, right? We can't have negative height. So we could estimate that it's going to take just after 4 seconds for the ball to come down. So the ball is in the air approximately, we'll say 4.1 seconds. Okay, part C says use the graph to estimate the coordinates of the vertex of the relation. Explain the meaning of the coordinates of the vertex in this context. So remember, going back to our definition, which is at the top here, so the vertex is the lowest or highest point on the parabola. Okay, so we can see the highest point on our parabola occurs right here, right? So the coordinates of that point are 2, 21.5. So it occurs at 2, 21.5. Okay? And what that is the highest point of the ball. Highest point of the ball. Now you have to always relate back to what the question is actually asking you. And last part here, it says explain the meaning of the data in the first row of the table. So the first row of the table. So that's talking about this coordinate point here. So our point 0, 1.5. So our time is 0 and our height is 1.5. Okay, so what that actually is telling us, obviously we don't throw a ball from laying on the ground, right? We're not laying on the ground and throwing the football, we're standing up. So that means that the ball was thrown from a height of 1.5. So when this person threw the ball, obviously where their hand kind of went as they thrown was at a starting height of 1.5. So the ball was thrown. Okay, so don't think of it as them standing on a platform of 1.5. Simply, obviously, your hands. This person's hands are 1.5 meters high from the ground. Ball was thrown from height of 1.5 meters. Okay, and this is the end of our first lesson of our second unit on quadratics.